Hello, and welcome back to some more structural engineering. For today's exercise, we're going to start delving into finding support reactions. We're going to start off today with a simple exercise. We're going to have a simply supported beam with one point load. Once we figure that out, we can move on to more complicated things. The main thing to consider is that we can only solve right now using equations of equilibrium. We have three equations of equilibrium in 2D, meaning we can only solve three unknown reactions. And that is going to be the basis for what we're going to do in the next couple of exercises. So without further ado, let's get to it. So this is my exercise. I've got a simply supported beam. You can see it's 4 meters long in total. At A, I've got a support. At B, I've got a support. Let's first clarify what those supports are, draw this in a simplified manner, and solve the reactions. Let's start off by drawing the beam. So I'm just going to draw it here, just as a schematic of the beam, okay, without too much detail. I know that I've got this force of 10 kilonewtons here, and that the distances are 3 meters and 1 meters. I'm doing this to draw my free body diagram, and that means I'm just looking at the forces, okay? So I'm stripping the structure of anything that I don't need just now, and looking at what the reactions are. At A, I can see that I've got a pin support. A pin support means that at that point, the structure is held in two perpendicular directions. So it can rotate, but it cannot move. So in this case, I'm going to have a reaction here of AY and a reaction here of AX. I'm drawing all of these according to just a positive X, Y axes. At point B, I can see those little wheels. I know that this is a roller or sliding support. And that means that at point B, there is only going to be one reaction. That reaction is going to be perpendicular to the ground. Okay, so it's going to go in this direction. BY. Because what this reaction means, it's a bit like a skateboard. I can move in the direction of that yellow arrow, right? I can skate, but I won't sink into the ground. And now that we have our free body diagram, we can solve using the three equations of equilibrium. Let's start off by looking at the sum of forces in the x direction. That has to equal 0 for this to be in equilibrium. So in the x direction, I can see that I've got AX, that's in the positive direction, and I don't have anything else. So AX has to equal 0. I'm going to move on now to the y direction, with this being my positive y, and I can see here that I've got AY positive plus BY positive minus 10 equals 0. And that's really all I can say now. I know that AY plus BY have to equal 10, but I can't really tell what either of them are. I'm going to have to solve another equation to find that. So if I go to my last equation has to be a sum of moments. This is the positive direction of moments according to our sign convention, so counterclockwise. The question is now, where do I do moments? Now, in reality, I can do moments wherever I want, but usually I will tend to choose a point where lots of forces pass through. Because as you recall, to get a moment, you need a force, but you also need a distance. So at a point where forces pass through, there is no distance, and therefore those forces passing through the point cannot contribute to moment. So I'm going to choose point A, because I can see that AY and AX pass through it. Sum of moments around A equals 0, so the only two things I have contributing to moment is the 10 kilonewtons and BY. Let's start off with the 10 kilonewtons. Using the right-hand rule to create a moment around A, I can see that this 10, this is its line of action, needs to go back to A, is going to create a negative moment, right? It's going to create a clockwise moment, which is in opposite to the direction that I've defined as positive. So let's start off by defining that. So minus 10. The next thing I need is the distance. The distance in this case from the line of action of 10 to A is 1 meter. Now I want to clarify something, right? When I have a force, the distance is always the perpendicular distance. And that means that if I have a force in y, I am always going to need a distance in x. Likewise, if I have a force in x, the distance that I need is always going to be a distance in y. If I have a force that is xy, say this force here, the distance, since this has to be the shortest distance, which is going to be the perpendicular distance, is also going to be in the xy plane. And that is why I find it very useful to just divide into components, because you always know that if you have a y component, you need an x distance, and if you have an x component, you need a y distance. And we'll cover that in the future. But for now, I've got that minus 10 times 1. by, I can see here, is going that line of action and then has to return to A. So it's creating what we would call a positive moment, because that is counterclockwise. So plus by, and the distance in x from the line of action of by to A is 4. And there is nothing else contributing to moment, since ay and ax pass through A. So looking at that, I can see that 4 by equal 10, and therefore by equals 10 divided by 4, or 2.5 kilonewtons. And once I have that, I can go back to my y equation, and I can see that ay equals 10 minus by, that is 10 minus, we now know, 2.5, and that gives me 7.5 kilonewtons. Let's draw that in and do a quick sense check. So if I return back up here to my original beam, I found out that ax was 0, so I can get rid of that. I found out just now that ay is positive, which means that this direction upwards that I assumed is correct, 7.5 kilonewtons. And I also found that by also came out positive. So again, the direction I assumed is correct, 2.5. Now I can see that 7.5 and 2.5 sum up to 10. So on that aspect, that is good. I can also see that closer to the force, that 7.5 is bigger than the 2.5, which is further away. And just intuitively, that makes sense. I can do one last check by doing the moments around B. They have to sum up to 0 as well. So let's do a quick check. So once again, this is my positive direction. Let's see what we get. Around B, this point here, I've got 7.5. Now, if you can see, that's its line of action, and then it has to come down to here. So it's creating a negative moment according to the right-hand rule. So minus 7.5 times the distance. The distance is the distance from the line of action to the point. So since that force is in y, I know that it's the distance in x, which is this distance here. So times 4 meters. Then I've got the 10, which this is the line of action of the 10, right? And then it has to return to this point here, to point B. So it's giving me a positive moment, or a counterclockwise moment, so plus 10, and the distance is the distance between its line of action and B along the x-axis, since it's on y, and that is 3 meters, so times 3, and that works out as minus 30 plus 30, and that is indeed 0, just as we're expecting. So tick there, and I can assume that my results are correct. So that was a discussion on how to approach reactions and how to solve them for a simply supported beam with one force. Join me again as we make things a bit more complicated and solve some more structures. Bye for now.